I will go through in this presentation a little bit about surface-free energy theories, and then at the end also link surface-free energy into practical applications. So let's start. Again, Henny gave us a presentation on contact angle measurements, and that is of course super important for the surface-free energy calculations, as well as that is really the basis of it. So as Henny said, we can measure a contact angle of a liquid on a solid surface, and when we talk about surface-free energy measurements, we typically do this with an optical method. So there are other methods to measure contact angles, but for surface-free energy calculations, you most typically want to use the static contact angle. So that's why we use the optical tensiometer to measure that. The reason why we want to, instead of just measuring the contact angle, we sometimes want to actually look at the surface-free energy of the solid, is that when we measure the contact angle, that you always have to mention with which liquid you have done the measurement. So contact angle is not in that sense like a property of a solid. It's a property of a liquid solid pair, or even maybe you should mention that it's a property of all three phases combined, so liquid, gas and solid. Typically this gas is air, and it doesn't have a huge influence on the contact angle results, but definitely the liquid used for measurement has a big influence on the contact angle results. So the reason really then to measure the surface-free energies is to have some sort of a value that is independent of the liquid, that is just describing the solid in a similar way as surface tension is describing the liquid. So the surface-free energy is really equivalent to surface tension of a liquid, and it actually arises from the same type of molecular interactions as the surface tension of a liquid. So if we think about the solid surface, let me just take a pointer here in use so it's a little bit easier to explain this. But if we look at this bulk interactions in the solid, again there is a net force of 0 affecting on the molecules in the bulk, whereas at the surface you have an excess force which gives the surface free energy of the solid. And when we have surfaces like metal surfaces, the surface-free energy is typically quite high, because there is, or at least theoretically, it should be quite high, because there are metallic bonds in between the metal atoms, which causes a higher surface-free energy, whereas in polymers the surface-free energy is typically lower because you have a weaker interactions in between the molecules. Now how we then measure the surface-free energy, and the answer is actually we don't really measure it, we have to calculate it. So if we look at this in the here the three-phase contact point between the in this three-phase contact point where we have the solid, liquid and gas in contact, we have different forces affecting on this contact point. So we have the surface tension of a liquid, we have the interfacial tension between solid and liquid, and then we have the surface free energy. And the balance of these forces can be written in this form, and this equation is called Young's equation. And in this, if we would solve here then the surface free energy of the solid, we would have on this side of the equation three unknowns. So we have the surface tension of a liquid, we have the contact angle between the solid and the liquid, and then we have the interfacial tension between solid and the liquid. And now, as you have seen in the previous presentations, the surface tension of the liquid we can fairly easily measure. The contact angle between solid and liquid we can also measure, but what we cannot really measure is the interfacial tension between solid and the liquid. So this is what we need to now model. And there are many different ways how we can model the surface, this interfacial tension between solid and liquid. And below in the list here, these are the methods that are the typical methods that we have for surface free energy calculations. So I will go through the most important ones a little bit more in detail for you to understand how the calculations are done. And now I will warn you that there will be a little bit of mathematics here, but just bear with me here, because this is quite important for the understanding of the theory behind. So when we start to think about this, how do we solve this? How do we solve this interfacial tension? How do we try to access this interfacial tension between solid and liquid? Let's start by looking at work of adhesion. So this is also a Dupree equation. And here we have a system. This is just a simplified schematics of a system where we have, let's say, an A and B, and there is an interface between those two. So then there is some sort of an interfacial tension between the parts A and B. And if we separate them, what we actually do, we create two new interfaces. The other one is between the part A and the gas phase. The other one is between the part B and the gas phase. So how much work has to be done to separate these two interfaces from each other is called work of adhesion. So we have here the work required to separate the two components from each other, and that is basically the surface tension of component A plus surface tension of component B minus the interfacial tension between those two components. Now, if we think about it so that the part A is the solid and part B is liquid, then we can change these symbols here so that we are actually looking at the work required to remove the liquid away from the solid. And then what we get is the surface tension or surface free energy of the solid plus surface tension of the liquid minus the interfacial tension between those two components. And now how we get then further, we can combine these two informations. So we have the Young's equation, and then we have the Dupree equation. And if we combine those two equations together, we get to an equation which is called Young-Dupree equation. And here we can actually see that we can calculate the work that is required to remove the liquid from the solid by if we know the surface tension of a liquid and we know the contact angle between the solid and the liquid. And this is really the basis of all, or let's say at least most of the surface free energy theories. And just to little bit remind you though is that since we are typically using static contact angles to calculate surface free energy, so independent of the surface free energy theory, you typically use static contact angle to do the calculations. There are certain assumptions that we need to do to be able to do these calculations. And the first one of them is that all of these approaches really rely on the validity of the Young's equation. So the Young's equation is the basis of the theories. Also, what is important is that we always use pure liquids. So when we do the contact angle measurements, we need to use pure liquids like pure water, pure solvents, because the surfactant solutions or different type of mixtures of liquids would basically just introduce quite a lot of complexity into the systems, because there would be most probably some sort of preferential absorption of liquids on the surface and due to these different molecules in the liquid. We also need to assume that throughout the measurement, the surface tension of a liquid, the surface free energy of the solid, and the interfacial tension between solid and the liquid are constant throughout the measurement. So this basically means that there shouldn't be any physical or chemical reactions between the solid and the liquid when we do these measurements. And of course, the surface tension of the liquid should be higher than the anticipated surface free energy of the solid. And this is because if you have a lower surface tension in the liquid, what will basically happen is that it will completely spread on the surface, and you wouldn't really be able to measure the contact angle, or you would need to mark the contact angle to be 0, and then the equations wouldn't really work anymore. And then the values of basically the values of surface free energy are kind of assumed to be constant from liquid to liquid. So basically the liquid shouldn't affect the surface free energy of the solid, which is of course I mean, in a sense kind of you know, given, or you can understand that we are now looking at the ultimate value for the solid, which is independent of any liquids used. So then if we start to go through one by one different surface free energy theories. The first one that I'm just going to mention is a Tishman plot, because this is, you might come across to this in the literature. But Tishman plot is not really a surface free energy measurement in a sense, because what you are actually getting from the Tishman plot is let's say the critical surface tension value for the liquid that will completely wet the surface. So how this is done is that you have your solid surface and you have a set of different test liquids with different surface tension values, and then you place the droplet of each liquid on the surface, and you measure the contact angle against the liquid and the solid. And when you reach the contact angle of 0, so basically the cosine of the contact angle is 1, then then if we look at the equation, the Young's equation, so if this goes to, this term here goes to 0, then basically the surface free energy is equal to the surface tension of a liquid. So this is how it's not really in a sense calculated. It's more according to measurements with several different probe liquids. But this is not super typical method, at least any longer, and it's also quite time consuming because you have to measure with several different probe liquids. Yeah, and this is just what I explained here, and this is basically what has been said is that Zisman plot works best for different type of dispersive surfaces, meaning polymer surfaces and things like that. But then and then another method that I'm going to briefly mention is called equation of state, and this is quite a controversial measurement method. This basically claims that by measuring a set of contact angles, you would be able to, or this is actually an empirical method in a sense that the equation of state, and especially this multiplier here, is based on the set of contact angle measurements done on several standard solids, and this claims that by just measuring one contact angle measurement, we would be able to access the information about the interfacial or interfacial tension, but then between solid and liquid, but then also the surface free energy of a solid. But as said, this is not very much used. But most of the, if we now move on to more typically used surface free energy theories, they are basically all based on the idea that we have different types of interactions on our surfaces in between the molecules of the materials. So we can divide the surface free energy into different components based on the interactions between the molecules. And here we would have then the dispersive interactions, polar interactions, then hydrogen interactions, acid-base interactions. There is a bunch of other different type of interactions involved here. And then it depends on the theory a little bit which interactions are taken into account. And the first method that I introduce here is called a simple Fogs. And what this method assumed actually is that we can omit all the other interactions here except the dispersive interaction. So this assumes that the surface free energy is only composed of dispersive interactions. And when we have that, then this is the form where we can write the interfacial tension between solid and liquid. So basically all of these theories that I'm going to talk now, they are trying to set some sort of an equation to this interfacial tension between solid and liquid. And here, if we then assume that the total surface free energy is equal to the dispersive part, so then we can also replace this term with the dispersive part. And I think in the next slide I have then combined this with you can then combine this with the Dupree equation, and this will lead to this type of an equation where we have the dispersive part of the solid, dispersive part of the liquid, and then we have the contact angle between solid and the liquid. So now if we would use, for example, water to do the measurement, then we would take the dispersive part of water, which is actually known from the literature, and then we would measure the contact angle with water on that solid, and then use that to do the calculation. So this would then require only to do one contact angle measurement with one liquid with known dispersive component on your solid. And but again, this method is not very widely used, since in most cases you don't have only dispersive interactions, you would also have polar interactions on your solid, or between the liquid and the solid. So this then leads to a theory that is probably the most used surface free energy theory at the moment, and this is called OWRK, which comes from the first letters of the persons that have been part of inventing this theory. And how did they then consider these interactions at the solid? Is that the surface free energy of a solid is, as I already showed, a sum of all these different type of interactions, but they have decided then that they have the dispersive, there is a dispersive component, and then all the other interactions can be put together into polar interactions. And then they used the mathematical theory of geometric mean, which was actually also used in the simple Folks equation, where so that they can write the interfacial tension between solid and liquid into this form. And here again, this is then now combined again with this Young-Dupree equation. If you are interested, it's actually quite simple to just do it with the pen and paper and see how it goes, and then you get a little bit better understanding of the equations if you do it yourself. But here really what is significant here is that when we get the equation into this format, we can see that we have two unknowns here. We have the dispersive component of the solid and the polar component of the solid. And again, to solve this equation, we have then two unknowns. So we need to be able to measure the surface with two liquids with known polar and dispersive components to solve this equation. And again, it's very common that you can, you can find these type of polar and dispersive components of many of the liquids in literature. And most typical liquids here used are water, of course, because it has both polar and dispersive part. But then as another liquid, you need to use a dispersive liquid, which has a significant dispersive component. And this is a little bit of a challenge because, as I said in the assumptions, that you need to have the surface tension of the liquid that you use need to be higher than expected surface free energy of your surface. And for most dispersive liquids, this is not the case, because most dispersive liquids have a very low surface tension values, so close to, let's say, 20 millinewtons per meter or even below. And in most of the surfaces, if you would put that sort of a drop on the surface, it would basically spread completely on the surface, and then your contact angle value would be 0. So this is the reason why most of the time when we measure surface free energies, we need to use quite exotic dispersive liquids. The most commonly used is diiodomethane. I'm just going to briefly mention this one. This is a what is called a Wu method. It's also used to some extent to calculate surface free energies, but this actually thinks about the interactions, the molecular interactions at the on solid and liquid exactly the same way as the OWRK. So there are polar and dispersive components involved, but instead of using this geometric mean model, Wu actually uses a harmonic mean model as a combination rule, which then leads to a slightly different looking, and actually, in my mind, actually a little bit more complex looking equation. But again, in reality, there are only the dispersive and polar components of the solids and liquid in the equation. And the same way as with the OWRK method, the Wu method can be solved if you measure the surface, if you measure the contact angle with two liquids with known polar and dispersive components. Then I think this is the last method that I'm going to mention, and this is called acid and base method. And this one basically continues a little bit of this this interaction theory, in a sense that it has the same dispersive part, so that's kept the same, but then it divides the polar part in the acid and base components. So then this will actually lead into an equation where you have three unknowns. So you have the dispersive part of the solid, the acid and base components of the solid. And to be able to solve this equation, since there are three unknown parameters, you need to do the contact angle measurement with three different liquids with known components. So now, again, you need to go one step further. So you need to be able to have or use liquids where these acid and base parts are also known. And again, most typically you would use water because it's a well studied and documented liquid. You would use diiodomethane. It actually doesn't have a polar part at all, so then of course you don't have the acid and base parts either. But then you would use maybe some other polar or slightly polar liquid like ethylene glycol or glycerol or something like that to access these surface properties. I think here I have a little bit summarized this in a table format, these different surface free energy theories. Those of you who paid attention in the first slide, you could see that there were also some others that I didn't even talk about, like salts, and I'm sure there is even more more of the methods that I didn't really mention. That's because those are extremely rare. Salts, for example, is not in an air liquid solid system, but in a liquid liquid solid system where you would do this type of surface free energy calculations, and that's quite uncommon way to do it. But here you can see the ones that I did discuss. So there are, I would say that the first three are very seldomly used, and the last three that I talked about, they are these kind of multi-component approaches, which are used much more than the others. And I would say the OWRK is probably the most commonly used method. In some cases, it has been claimed that the WU method would actually work better for polymers, but if you look at in this contact angle measurement softwares, where you can see the results with different theories, the OWRK and the WU method are very close to each other typically. And then there is an acid and base method, which gives you this third dimension information. And this is something that is actually quite commonly used when we are studying biomaterial surfaces, for example, because cells are known to behave differently on acid or base surfaces. So this is in that context, the acid, you can also see the acid and base theory being applied. But let's spend the remaining of this talk by looking through a little bit how surface free energy can be used in practice. And the reason really why people would be interested in measuring surface free energies is to understand better wettability and in that sense also adhesion of different coating formulations on your surface. And if we want to achieve a good adhesion between a solid and the liquid, then we do need to have a good wettability because the coating formulation needs to spread on the surface. This is giving more possibilities for mechanical bonding, but also we need to if there are these, let's say, voids between the coatings, so if the wettability is not good, this is a super simplified picture, but if the wettability is not good, there will be these voids between the coating and the substrate, which will lead to fewer available binding sites. And now surface free energy is linked here because basically surface free energy of the solid should always be higher than the surface tension of the coating formulation. So this is kind of the how we achieve a good wettability. Another thing that should be mentioned here is though that surface also need to be clean. So if there are any organic contaminants or if there are loosely bound dirt on the surface, this will of course diminish adhesion because then you have the coating formulation is not actually attaching to your substrate, but it's attaching to the dirt or contamination, or in some materials, if you have loosely bound native oxides on surfaces, that can also be a problem and cause adhesion failures later on. So if we look at some examples of different materials, so here is just a list of some different type of materials like glass, metals, different polymers, and then below some different type of solvents and resins. And if we think about the requirement that surface free energy of this solid has to be higher than the surface tension of the coating formulation, then we can see here that in some cases this is true on a native surface, but especially if we think about polymer surfaces, these surfaces have often way too low surface free energy values to accommodate the liquid spreading on them. And then there are, of course, different ways what we can do to overcome this challenge by either changing the coating formulation or modifying our solid surface somehow to get the surface free energy up. One thing here to note, though, that for glass and metal surfaces, it shows quite high surface free energies, especially for metals. Theoretical surface free energies are extremely high because of these metallic bonds in the material. But of course, if we bring that type of a high surface free energy solid into basically take it outside of vacuum, if we bring it in contact with air, it will immediately be contaminated because there is this tendency to lower these energy values in nature. So you cannot really measure these high surface free energy values for metal surfaces in a normal lab environment. And this is also sometimes why it's quite challenging to make, any kind of, I mean, there are, of course, databases which show surface free energy values, but, and maybe for polymers, it's a little bit easier because they tend to be quite low, but it is quite challenging to say if you just buy a piece of metal from a store that the surface free energy of this is this and this value, because it is so dependent on storage conditions, cleanliness of the surface, roughness of the surface, etc., etc. Yeah, this one I already a little bit went through. So of course, when we are thinking about a situation where we would like to be able to do some sort of a coating of the surface, and we can see maybe we have done our measurements, we see that okay, it actually looks that the surface free energy is way too low for this coating formulation. So then you have two options. You either modify the solid by some sort of a surface treatment method, or then you modify your coating formulation maybe by adding some wetting agents to lower the surface tension value of your formulation. One thing that I want to mention now, I have been talking only about in these examples, the surface free energy and surface tension as a one number. But as you saw in the theories, we actually do divide the interactions in the polar and dispersive components. So then it is possible to go further than just looking at the surface free energy value and the surface tension value as one number. You can also look at actually match the polar and dispersive interactions of your solid and liquid, because in principle, if these polar and dispersive interactions match, then you have a better wettability of the surface, because you have a more interaction between the solid and the liquid. So there is also a possibility to, with the same equations as we use for calculating the surface free energy of the solid, we can also calculate the surface tension components of the coating formulation by measuring the total surface tension of the formulation and then measuring a contact angle of this liquid against a completely dispersive solid with known surface free energy, and typically that solid would be a clean polished Teflon surface. So then we could we could also understand the polar and dispersive and interactions in our coating formulations, and then we would be able to use tools like wetting and adhesion analysis, which is in the software, where we can list all our solid surfaces and all our coating formulations, and we can check based on the polar and dispersive interactions, which one of the coating formulations would completely wet your solid, just by based on theoretical calculations, rather than doing multiple contact angle measurements for each solid liquid pair. So I think with this I am coming to the conclusions, and so surface free energy is something that we cannot measure directly, unfortunately. We need to do it through contact angle measurements, and then we need to actually apply apply a theory that allows us to get access to this solid liquid interaction, and most commonly used theory for that is the OWRK theory. And to get good good adhesion, this surface free energy is important to understand, because we need to have the surface free energy of the solid higher than the surface tension of the coating formulation. And then there is also a possibility to use different type of or to use this type of a wetting and adhesion analysis tool to really cross-reference multiple solids against multiple different liquids to see how they will interact, at least in a theoretical sense.